All right, everyone, welcome to our series on ultrasound transducer management. We're going to start off our series with the knowledge of transducer components, which we'll cover in this little recording. That'll be followed up by frequency relationships and transducer selection. Then we're going to move on to 2D array transducer concepts and then 3D and 4D concepts. So let's go ahead and get started. Okay, so question number one says the transducer element converts blank to blank and vice versa. And the answers available are A, voltage and electricity, B, pulses and ultrasound, C, ultrasound and voltage, and D, electricity and ultrasound. Now, the correct answer that they're looking for here is D, electricity and ultrasound. So let's talk about why that's correct. So the transducer element operates by piezoelectric principle. So it performs two-way energy conversion. So transmission and send mode, which is electrical energy turned to mechanical vibration, which then turns to ultrasound waves. Then you have the reception, which is the receive mode. So the returning ultrasound, so mechanical deformation of the crystal gets converted to an electrical signal. So the element converts electricity to ultrasound and ultrasound back to electricity. And that's kind of the entire basis for imaging, and that's the way it's written for sonography. Some of your engineering folks might debate why one of the other answers might be correct or incorrect, but again, this is for the SPI. Now let's go ahead and jump into why the other answers are incorrect. So the first one was voltage and electricity. So voltage, and they're saying is electricity here. So this answer is just basically saying electricity equals electricity. So that's not a form of energy conversion. It kind of ignores the mechanical sound portion entirely. B was pulses and ultrasound. So electrical pulses are applied to the element, but the pulses are not the form of energy that's being converted. The element converts electrical energy, not just the pulses, into mechanical, which is acoustic energy. And so that answer is incomplete and a little bit imprecise. The other one is ultrasound and voltage. Again, this only describes the receiving half of the process. So yes, returning ultrasound is converted into voltage, but the question says converts blank to blank and vice versa. And so that means it has to describe both directions. So only answer D is that properly captures the full bidirectional conversion. So something you want to consider with the SPI exam, if you see something that says and vice versa, or send and receive, or transmit and detect, they're testing whether you understand the two-way piezoelectric process, that the crystal always converts electrical energy to mechanical ultrasound energy, which is basically the heartbeat of ultrasound physics. Okay, so the next one says the transducer has an impedance blank times that of tissue. And answer A is 4, B is 10, C is 20, and D is 6. Now I know I generated images that sort of give you the answer. So in this case, the correct answer is C, 20. So acoustical impedance, which is denoted by Z, is equal to the density and propagation speed. So it determines how much sound is transmitted versus reflected at any boundary. So soft tissue impedance is about 1.5 megarails. Piezoelectric crystals, the PZT impedance, that's about 30 megarails. So if you divide that 30 by 1.5, you get 20. So the transducer element has about 20 times the impedance of tissue. And so again, that's a huge mismatch. So, which is exactly why we need that matching layer in the probe. So without it, almost all of the sound would just reflect back into the crystal instead of entering the patient. So let's look at why the other answer is incorrect. So A says 4. Again, that's too small. If it were only 4 times higher, transmission into the tissue would be much more efficient, and we wouldn't need such carefully engineered matching layers. So real impedance mismatched, again, is much, much larger. Answer B was 10. Again, that's a little closer, but it's still incorrect. 10 times would be a significant mismatch, but measured values show the crystal was closer to about 20. Right, and it's greater in softer tissue. D said 6. Again, also too small. It doesn't reflect that known physical properties of the piezoelectric crystals compared to human tissue. And again, this is clinically important. Just it matters clinically because if the impedance mismatch were not corrected, nearly again all of the sound would reflect at the transducer skin interface. So image brightness would be extremely low, diagnostic ultrasound wouldn't work effectively, and that's why we use that matching layer, the impedance halfway between the crystal and the tissue. And then when you use the gel just eliminates the air or any of the little pockets which would reflect about 100% of that sound. So a good memory trick, tissue is about 1.5, crystal is about 30. Again, 30 divided by 1.5 is about 20. So, or it's 20. So just remember that, and you're always gonna do fine on a question like this. All right, let me zoom in. The next question. The matching layer, A, reduces reflection of ultrasound at element. B, reduces transmission of ultrasound at element. C, increases reflection of the ultrasound element. And D, increases the spatial pulse length. Right, so the correct answer in this case is A. Right, so A reduces reflection of ultrasound at the element. And this is correct. Just remember that we talked about the piezoelectric crystal impedance being 30 megareals, soft tissue impedance being 1.5 megareals, so that's about 20 times mismatch. So without intervention, you get a huge percentage of the sound wave that would reflect right back into the crystal at that boundary layer. So we're looking at the matching layer's job. And it has an impedance in between the crystal and the tissue. So think of it like the middleman that smooths the transition. So by placing this material with intermediate impedance between the two, we reduce reflection, we increase transmission into the patient, we improve image brightness and efficiency. So yes, it reduces reflection at the element. Let's look at the other answers, why they're incorrect. B says reduces transmission of the ultrasound at element. So no. The entire purpose of the matching layer is to increase transmission, not reduce it. So again, this is just backwards. Reducing transmission would make imaging worse. C says increase reflection of the ultrasound element. Again, that's the opposite of what we want. More reflection at the crystal means less sound entering the tissue, and again, you're going to get poorer image. And then D was increase the spatial pulse length. So spatial pulse length, SPL, that depends on the number of cycles in the pulse and the wavelength. So it's mainly controlled by the back-end material, the dampened material, not the matching layer. So matching layers affect impedance, matching and transmission, not the pulse length. So if you think of crystal, the crystal, the matching layer, the gel, and the tissue in that order, each step reduces the impedance mismatch. So more energy moves forward instead of bouncing backwards. So if you didn't have a matching layer, you would have terrible efficiency. Okay, the next one is, and I hope you can see my eyes and they don't look like they're closed. What principle states that some materials produce a voltage when deformed by an applied pressure? So A says ALARA, as low as reasonably achievable. That's a principle, and not just for ultrasound, but for any kind of imaging. B is piezoelectric principle. C is Snell's principle, and D is Huygens principle. So the correct answer here is going to be B, right? The piezoelectric principle. So what is the piezoelectric principle? I'm going to just attack the question as if this is your only question that you're studying, and so I'll try to cover it thoroughly. Again, certain materials, they'll generate electric voltage when you apply mechanical pressure to it, and then conversely, when you deform the material, a voltage, correctly. You apply electrical, it deforms. When you deform it mechanically, it creates an electrical potential. Okay, so in ultrasound, electrical energy is created by the crystal deformation, and that produces sound waves. Electrical energy causes the crystal to deform, that produces sound waves. The returning echoes are pressure waves, so they actually mechanically deform the transducer, which ends up producing a voltage. So it goes in the other direction. So the same crystal both transmits and receives, and that's the entire foundation of how transducers work. So the common piezoelectric material, lead, zirconate, titanate, that's the common material. And if we didn't have any piezoelectric effect, you wouldn't have any ultrasound imaging not modern day. So I think some of the earlier devices may have worked differently. So let's talk about the other ones now. Why are they incorrect? Alara principle. Now this may seem like you see the word Alara, you might think, oh, that's got to be what they're looking for. This is a safety principle. It's not a physics principle. So Alara, remember, stands for as low as reasonably achievable, and it just refers to minimizing patient exposure to ultrasound energy. It doesn't have anything to do with voltage production from the pressure. You're probably thinking, why do we need to reduce ultrasound energy within a patient? Isn't that safe? It still produces heat. So just think about if you've gone to physical therapy and they use ultrasound to generate heat to, improve circulation and so forth. They operate on different frequencies, and so you don't want to do that with conventional ultrasound. They're still as low as reasonable achievable. Safety precautions. And let's keep going. The next one was Snell's principle. So again, this describes refraction. So it describes how a wave bends when entering a medium at an angle, and then it changes the speed. So it governs angle changes, not voltage production. And the other one was Huygens principle. And this explains how wavefronts propagate and spread. So it helps explain diffraction and wave behavior, but again, nothing about generating voltage. So the big concept here, or the conceptual separation, when you're looking at a principle and what it describes, piezoelectric, remember that's when you're going from voltage to pressure, or vice versa, from pressure to voltage. Snell's law is dealing with refraction, or due to angle change. Huygens is wave propagation, and Alara is a patient safety term. Okay, the next question. Electric blank applied to a transducer are converted to ultrasound. A is pulses, B is waves, C is echoes, and D is voltages. Okay, and so the correct answer here is voltages. And why is this correct? Well, ultrasound systems, they'll send electrical voltage pulses to the piezoelectric crystal. A voltage, when it gets applied to a crystal, it deforms the crystal. It causes it to oscillate, to expand and contract. That mechanical deformation produces waves or pressure waves, ultrasound waves, because they're very, very fast. And so the sequence, remember, it's electrical voltage, crystal deformation, mechanical pressure wave, which is the ultrasound. And the key word we're looking for here is voltage, because piezoelectric effect is specifically triggered by the applied electric potential. Look at the other answers again, why they're incorrect. Well, A says pulses. Again, tempting, but it's incomplete. Yes, we do send those voltages and pulses, but those pulses are specifically electrical voltage pulses, so pulses alone don't. It's too vague, in other words. Waves, electrical waves are not directly applied to create ultrasound in the transducer. We apply voltage, not ultrasound waves. The waves are the result of that input. Excuse me. And then C was echoes. Echoes, again, are returning sound waves from the tissue. So they're received by the crystal, they deform the crystal, and then it gets converted back into a voltage. And so those echoes are on the receiving side, not the transmission side. So again, a little simple model, a mental model to think of. On the transmit side, you have voltage in, sound out. On the receive side, it's sound in, voltage out. So again, same crystal, but you get two directions and one principle. All right, let's go ahead and read this question. I'm going to zoom in real quick. The critical temperature an ultrasound transducer cannot exceed is called the blank. And answer A is Curie point, B is quality factor, C is critical point, and D is piezoelectric point, or piezoelectric point. Okay, and so the correct answer is the Curie point. And so the Curie point is the temperature at which a piezoelectric crystal loses its polarization, it loses its piezoelectric properties, and it permanently stops functioning as a transducer element. So in basic terms, if the crystal gets too hot, it forgets how to be a piezoelectric. All right, so you have no polarization, no deformation with voltage, no ultrasound production. And once that temperature is exceeded, the damage is irreversible. For crystals, the Curie temperature is typically several hundred degrees Celsius. So um, it's when you overheat it with improper use, or maybe it has manufactured defects that'll um, cause that to defect even further. Have you ever heated a magnet and it loses its magnetic properties? So something like along the same lines. Let's look at the other one and see why they're incorrect. So B said quality factor, the Q factor. And the Q factor refers to bandwidth, damping, pulse duration characteristics, and it describes how ringy the crystal is, not the temperature limits. So it's very similar to the Q factor when we're dealing with inductors and electronic circuits, when you're dealing with capacitors and inductors. But again, the Q factor is, just to be clear, it's for inductors. C, the critical point, that's incorrect, right? It sounds fine, sounds scientific, but it's not a defined term that's used in ultrasound physics for transducers. So it's kind of a distraction or a distractor. So again, for those of you in electrical engineering that are looking at this, you've got to look at this from the point of how the SPI writes the exams and how the diagnostic medical sonographers interpret this. So you might be able to debate one of these answers in some of these questions, but just drop it and try to understand how they see it. D is the piezoelectric point. And again, this is not an actual technical term. The correct historical and physical term is Curie point. So that's named after, I'm not French, Pierre Curie, who studied the piezoelectric materials. So the big thing to remember here is that polarization of the crystal is what makes it work. So the Curie point is the temperature where that polarization disappears, and once polarization is gone, the crystal is just a piece of ceramic. Okay, next question is, which of the following is attached to the rear face of the transducer element? A, damping, C, ceramics, C, matching layer, or D, the coupling media? And the correct answer for this one is the damping. And let's talk about why that's correct. So the damping material is also called the backing material, and it's attached to the rear face of the piezoelectric crystal. So it absorbs backward directed sound waves. It stops the crystal from vibrating too long, and its main purpose is to shorten the pulse, reduce the ringing, improves axial resolution. And so without damping, the crystal would just ring like a bell, and it would produce a long pulse, and you'd end up with poor resolution. So the rear of the crystal, the damping, the backing material improves all this. And let's look at the other answers, why they're incorrect. B was ceramics. And so the crystal itself is a ceramic, it's PZT, but it's not attached to the rear, it is the element. The next one was the matching layer. So remember, this is attached to the front face of the crystal, and if you remember, its job was to reduce impedance mismatch. So that helps with the improvement of the transmission of the sound wave into the tissue. So the front is equal to the matching layer. The rear is where the damping is at. And answer D was coupling media. So this is a gel, right? So it goes between the transducer face and the patient's skin. So again, this is just used to eliminate the air or any air pockets or just gaps. That's what I was thinking of, air gaps. And that would, things that would reflect almost 100% of the sound. So it's external, it's not part of the internal transducer construction. So a quick mental note, for the front of the transducer is where the matching layer is at, and that goes to the patient. The middle is where the crystal is out. The rear is where the damping or the backing material is at. So again, front improves transmission, the rear improves resolution. All right, next question. Again, zooming in. Ultrasound transducers operate according to what? A, Snell's law. B, Huygens principle. I keep wanting to say Huygens. Huygens principle. C, the piezoelectric principle. Or D, the piezoenergy principle. So they kind of try to throw you off with this one, but we know the answer, right? So the answer is C, the piezoelectric principle. Again, ultrasound transducers, some water. They operate based on the piezoelectric principle. And what that says is certain materials, they'll generate a voltage when they're mechanically deformed, and they'll mechanically deform when you apply a voltage. So that's kind of exactly what that transducer does. In the transmit mode, there's an electrical voltage. It deforms the crystal. That deformation is actually producing an ultrasound wave that's getting transmitted. When you're receiving the ultrasound waves from the tissue, the receive mode, that's the returning sound wave. That's going to hit the crystal and physically deform the crystal, which then generates a voltage on the crystal. It's the same crystal, again, two directions, but one principle. Let's look at the other answers. Snell's law. That sounds like something from Lord of the Rings. I don't know if there's a snail in Lord of the Rings, but Snell's law describes refraction. It describes how sound bends when it crosses a boundary at an angle. So it's important in imaging physics, but not what makes the transducer work. Huygens principle, again, this explains the wavefront propagation and how it spreads. I don't know, I was making a word there. And what it does, it helps describe diffraction and beam behavior. Again, but it's not crystal operation. The other one is piezo energy principle. That, again, that sounds convincing. It sounds like a real term, but it's not a real term. It's not a physics term. It's just something they made to kind of throw you off. But it sounds interesting. It sounds like it could have been close to the right answer. So if you see a question asking how does a transducer work, what principle allows sound production, what converts electrical to mechanical energy, your brain should immediately go to the piezoelectric principle. All right, the next question, to zoom in. Shortening the pulses in diagnostic ultrasound broadens the what? A is bandwidth, B is duty factor, C is pulse duration, and D is lateral resolution. And the correct answer for this one is bandwidth, A. So again, when you shorten the pulse, you reduce the number of cycles per pulse, pulse duration, the spatial pulse length, and here's the kind of the key physics rule. Short pulses equals wide bandwidth. So long pulses equals narrow bandwidth. And you're probably asking, why is this? Because very short pulses contains a broader range of frequencies. And this is fundamental to wave principles. So short time signals spread out in frequency. So in ultrasound terms, heavy damping relates to short pulse. Short pulse relates to broad bandwidth. And broad bandwidth relates to better axial resolution. So if you shorten the pulses, that broadens the bandwidth. And let's look at the other answers. B said duty factor. So duty factor is equal to the pulse duration divided by the pulse repetition period. You should learn that in the very beginning of the ultrasound physics courses, or even in your general physics courses. So if you shorten the pulse, you actually decrease duty factor. You don't broaden it. So duty factor isn't something you broaden. C was pulse duration. So shortening the pulse decreases the pulse duration. The question asks what becomes broader. So pulse duration actually becomes shorter here. Lateral resolution depends on beam width, not the pulse length. So short pulses, they'll improve things like axial resolution, but not lateral resolution. So a good clean concept chain to think about: shorter pulses equals fewer cycles, which equals heavy damping. So that leads to broader bandwidth, and that'll lead to improved axial resolution. Okay, this is a very long one. Let's see. 43. The impedance of the matching layer is blank. A says an intermediate value between the transducer element and tissue. B says greater than the value between the transducer element and tissue. C says less than the value between the transducer element and tissue. And D says equal to the impedance of the tissue. And so the correct answer is the impedance of the matching layer is an intermediate value between the transducer element and the tissue. And let's think about like this, right? So remember the big mismatch, right? Crystal, the piezoelectric being 30 megarails and soft tissue being about 1.5 megarails, and having about a 20 times difference in impedance mismatch. Again, if we put them directly together, most of the sound reflects. So what do? We insert this matching layer whose impedance is in between the crystal and the tissue. So more specifically, we look at ideally matching the layer, the impedance layer. And so you can, if you remember this from your textbook, the impedance of the matching, so Z sub M, would be equal to the square root of Z of the crystal times Z of the tissue. So go back and look at your physics book. And what this does, it creates a gradual transition instead of a sudden jump. So what happens is you reduce reflection, you increase transmission, you improve efficiency. And so that's basically acoustic diplomacy. And let's look at the other ones, why they're incorrect. B said, greater than the value between the transducer element and tissue. Again, if it were even higher than the crystal, that would worsen the mismatch. So more mismatch, again, equals more reflection. And C was less than the value between the transducer element and tissue. Again, if it were lower than both, you'd still have a large mismatch. So the whole purpose is to sit in the middle, not at one extreme. And then D was equal to the impedance of tissue. So again, tempting, but again, it's incorrect. If the matching layer had the same impedance of the tissue, you'd still have a massive jump from the crystal 30 down to 1.5. And so that first boundary would reflect a ton of energy. And so the matching layer has to bridge the gap, not just match one side. Think of it this way. The crystal is about 30, matching layer is about, let's say, 7, somewhere in between, and the tissue about 1.5. So instead of one huge drop, you create like smaller steps. Less refraction and more sound that gets moved forward. Okay, next one. Sorry, I'm going to zoom in. The operating frequency depends on the element propagation speed and thickness. That's a true and false. Again, A is true and B is false. And so, again, the correct answer is true. So the operating frequency, the resonant frequency of the transducer crystal, we determined that by, remember, F is equal to C divided by 2 times T. F was the operating frequency, C was the propagation speed in the crystal, and T was the thickness of the crystal. So frequency depends directly on the propagation speed of sound in the piezoelectric material and the thickness of the element. So what this means physically, and again, if any of you design transducers, please leave a comment. The crystal vibrates most efficiently when its thickness equals about 1/2 the wavelength inside the crystal. That kind of sounds familiar. It kind of sounds similar to something called the Nyquist theorem, but I won't move into that. But think of this, they're not related, but I'm just saying it kind of does sound interesting. If you have a thinner crystal, you're going to have higher frequencies. If you have a thicker crystal, you'll have lower frequencies. And since propagation speed is part of the equation, it also affects the frequency. But let's look at why false is incorrect. So if we're reading the statement, we're looking at it from the other perspective. If the statement were false, it would imply that frequency is independent of crystal thickness, which again is not true. So the thickness is the primary design factor that controls the frequency, and that's why high frequency probes have very thin elements. Again, a memory trick. Higher frequency is equal to a thinner crystal, lower frequency is equal to a thicker crystal. And if you remember the little saying, thin sings high. Okay, next question. Damping material in pulsed transducers increases the spatial pulse length. This is a true and false. A is true, B is false. And again, the correct answer for this one is false. This is false. So the damping or that backing material, that's attached to the rear of the crystal, and its job is to absorb the backward directed sound. It's to stop the crystal from vibrating too long, so reducing that ringing. So when damping is increased, the number of cycles per pulse decreases, pulse duration decreases, spatial pulse length, that'll also decrease. So damping actually shortens the spatial pulse length, so it doesn't increase it. What spatial pulse length depends on, the SPL, is going to be equal to the number of cycles times the wavelength. So think of heavy damping, fewer cycles, shorter SPL. And shorter SPL actually equals to better axial resolution. But if the statement were true, and we're looking at it from the question from a different perspective, um, pulses would end up being longer. Axial resolution would just be the opposite. It would be worse. And that would defeat the purpose of damping. So damping improves axial resolution by shortening the pulses. And again, a clean concept, more damping, shorter pulses, shorter SPL. It also leads to broader bandwidth and then better axial resolution. Can you see my hands? Yeah. Okay, next question. Ceramics used as materials in the production of modern ultrasound transducer elements are naturally piezoelectric. A says true, B is false. All right, so guess what? The um, the answer for this one is false. And this might throw some people off with your initial instinct. Modern ultrasound transducers use ceramic materials like PZT or lead zirconate titanate. And these ceramics are not naturally piezoelectric. They have to go through a process called polarization. Remember we talked about how they lose the polarization with temperature. So what happens during polarization, the ceramic is heated near what's called, if you remember the term, the Curie temperature. So you have a strong electric field that's applied. The internal dipoles within the material align in one direction, and the material then is cooled while the field is still applied. And then it becomes piezoelectric. So without this process, the ceramic would just be ceramic. And let's look at it from the other direction. Why is true incorrect? Again, kind of like because this is not materials like quartz in nature, when those are naturally piezoelectric, right? Um, the ceramics that are used in modern medical ultrasound, these are synthetic and they require polarization. So that's the distinction that they're testing with this kind of question. Again, think of like magnetic materials that you can magnetize and demagnetize, like, and with temperature, kind of the same thing. So the big concept here to remember is that natural piezoelectric materials are things like quartz. We don't use quartz for ultrasound transducers. We use PZT. It's a ceramic. It has to be polarized. So again, if we don't have any polarization, you can't have any voltage production and then no ultrasound. Okay, next question. Various formulations of lead zirconate titanate are commonly used in modern day transducers. A is true, B is false. And again, the correct answer is true. So again, these questions are related, and so one question right after the other, it might seem like we're repeating ourselves, but I did this on purpose, where I put the questions by topic, and then the ones that are related, I try to put them close together, so you can hear this repetition, questions asked in different ways, so the concept would sink in. Okay, so let's look at why this is true. So modern diagnostic ultrasound transducers, they commonly use lead zirconate titanate. And again, I might be mispronouncing it. We use that as a piezoelectric material. Again, and not just one type. There's several different formulations of PZT. Again, you can change the composition slightly, and this is going to allow manufacturers or materials engineers to change the sensitivity, the bandwidth, the efficiency, mechanical strength, temperature stability. So everything that a materials engineer, when they work their magic with materials, what they can do. Awesome people who create all of our stuff, our PZTs, our resistors, our you name it, our semiconductor materials engineers are where would we be without them? Anyway, back to the question. So we have different clinical applications like cardiac, vascular, abdominal, high frequency probes, right? And so they require slightly different performance characteristics, and that's achieved by tweaking that PZT formula. Again, something you don't have to do, just know that it's done There are materials engineers, and this is what they live for. They cook. All right. And if again we're looking at this, and let's say you initially think of this as incorrect, so let's walk through that rationale. Again, if this were false, it would suggest that PZT is not commonly used, which again that's just flat out incorrect. PZT is. It's the most widely used piezoelectric ceramic in medical ultrasound. It's engineered again in various formulations for optimized performance for a particular type of scan. And takeaway from these last couple of slides, quartz, remember that was a natural piezoelectric. It's older technology. PZT is synthetic. We have to polarize it for it to become piezoelectric. We can also customize it. So modern ultrasound, we use engineered ceramics, not natural crystals. All right, the last question in this presentation or recording. Wide bandwidth allows harmonic imaging. Again, another true or false. A is true, B is false. So this one is true. Wide bandwidth allows harmonic imaging. And so why is this true? So what is harmonic imaging? Harmonic imaging, that depends on receiving frequencies that are different from the transmitted frequency. So when we transmit a fundamental frequency, for example, 2 megahertz, the body generates harmonic frequencies like 4 megahertz, and then a second harmonic. If you remember this from your signals courses in electronics for your electrical engineers, and again, in your ultrasound physics class for your sonographers, if we looked at the harmonics of a particular frequency that it generates, if you remember first, third, fifth, seventh harmonic, or second, fourth harmonics, right? They end up being smaller in amplitude, and they end up being a multiple of the frequency that's initially generated. Anyway, back to the question. To both transmit and receive these different frequencies, the transducer has to have a wide bandwidth. So because, again, bandwidth is going to be equal to the range of frequencies that the transducer can effectively transmit and receive. So if the bandwidth were narrow, the system would only handle a very tight frequency range, and it couldn't properly detect harmonics. And harmonics we can make use of harmonics. We do all the time. Now let's look at this question from the other perspective. If you initially just thought false, kind of teaching you how to look at questions like this, and why not fall into this trap. So if you looked at it and you thought false initially, so remember that if the bandwidth were actually narrow, the transducer would struggle to receive harmonic frequencies. I'm kind of saying this backwards from what I said earlier. Harmonic imaging would be inefficient or would be impossible. So wide bandwidth gives you more flexibility, and then flexibility gives you better harmonic capability. So think of it like a few things to keep in mind from everything we talked about. First, starting off with things like heavy damping, right? We know that heavy damping shortens pulses, and that leads to a broad bandwidth. Broad bandwidth actually supports harmonic imaging. Harmonic imaging leads to improved image quality, so things like less noise and better resolution. So hopefully this is the last slide. Hopefully this last question kind of put a lot of those little concepts together. Thank you very much for your time. See you on the next topic.